This is lesson 4.4, Congruence and Transformations. We're going to be looking at different congruent figures and the different congruences we can have whenever they've been transformed, like what we've already done in translation and rotation and reflection. And so then we'll just be able to look at different problems that apply these properties. So congruent figures work just like the word congruence that we've seen before. Congruence means that they're the same size and the same shape. So when we have congruent figures, when we transform them using just our rigid motions or rigid movements, then they will always still be congruent. So the rigid motions that we've covered is translations, reflections, and rotations. We can also combine any of these. And so if I do a translation and a reflection, those figures would still be congruent. If I do a reflection and a rotation, again, they would still be congruent. So in this example 1, we just want to be able to identify any figures in this picture that are congruent, that are the same size and same shape. So first I'm going to key in on these squares. I have this square of ABCD. And so it is just a quadrilateral ABCD. And then I have this other one down here as well of NPQR. These are squares because both sides are the same length. I have a 2 by 2 square here and a 2 by 2. So they would appear to be the same size and same shape. So I could say that these figures would be congruent using my congruent symbol. And so I would say ABCD is congruent with NPQR. And it would appear in this case that they were simply translated. They were moved to the left some, so on our x-axis we would have subtracted what looks like 2, and then they would go down, which would be subtracting from our y-axis as well, so it would be translated. Next I'm going to key into this triangle of EFG, so triangle EFG. If I notice this side has a length of 3, this side has a length of 2. So it would appear, if you look down at MKL or LKM, whichever way, it also has a length of 3 on one side and a length of 2 on the other. So it would appear that this was simply reflected. So a reflection would just be reflected across. They're both the same distance from the x-axis, so they were simply reflected across the x-axis. So these two would also still be congruent, since they were simply reflected. So I have EFG would be congruent with triangle LKM or KLM, whichever way. And typically I would actually line up the letters that are in the same position, so I would actually erase this and actually call it KLM, so that way they're still in the same order. Because E and K are in the same position when they're reflected, L and F are in the same position, and then G and M would be in the same position. So then our last set of shapes is going to be that one more triangle that we have up there. So we have triangle HIJ. And the only one that we have left in this picture is also this triangle over here of UST. And so if I look once again, I have a length of 2 and 2. I have a length of 2 and 2. They're right triangles. So these are congruent. They're the same size, same shape. So I could say that they are congruent. And it would appear that these ones were rotated. This would be rotated 180 degrees all the way around. And it was just rotated around the origin. So each of the ones in the last example were simply, they went through one transformation. We had a reflection, we had a rotation, and then we also had a translation. When we have congruence transformations, we can also have them that have a combination. So they, like we said earlier, they could also be translated and reflected. They would still be congruent. The pre-image and the image would still be congruent because they went through only rigid motions. And so in example 2, we can actually see where we have several different combinations of transformations. So when I look first at this picture, one thing that I could think at first would be that it was rotated. But I do want you to notice that we have acute angles here of A and C. But our angles down here on this other shape are G and E. If it was rotated, then the acute angle would still be on the inside. It would be close to the origin, the same distance from the origin right here. But instead, if I look here, I don't have that A right there. I don't have a similar point there that has that acute angle. So this one obviously has to go through at least 2 different transformations. So since it ended up looking like it's flipped, if you notice how the acute angles are on the bottom left and then the top right of this picture, on my other one, they are actually on the top left and the bottom right. So it looks like it was reflected. So first, I'm going to look at reflecting it across the y-axis. So if I reflect it, I'm going to have this point. This would be my A prime. D was 2 away, so here I would have D prime. And so when I've reflected all 4 points, I have this new shape of A, B, C, D, all with primes on them. And now, if you compare this shape that I reflected to the one at the bottom, it looks like the shape hasn't changed, it simply has shifted down. So whenever it's shifted, that will just be like translation. And so for translation, this one would be a vector of moving down 1, 2, 3, 4. So it would subtract 4. It didn't move left or right any, so this was simply subtracting just from our y. So my vector in this case would be 0, negative 4. So if I want to describe my congruent transformation, I would say that first, rectangle ABCD is reflected across the y-axis, and then translated down 4 units. So that would describe my congruent transformation. EFGH is congruent still to ABCD. Okay, it simply just was reflected and then it was shifted down. So when we think about congruence, we can reflect images across any line. Now typically we think about them as being reflected across the x-axis or the y-axis, or common lines like our y equals x or y equals negative x. But we can reflect a shape across any line, any given line. In this theorem, reflections in parallel lines theorem, it simply tells us if I reflect an image across a set of parallel lines, so I reflected across the first one, in this case line K, and then I reflect it again across M, it's going to result in a translation. So if I look just at this first line of A, B, this line segment A, B, and I look at it going all the way to A double prime, B double prime, then this would result in a translation. If I look at it simply from that first set to the second one, if I take out that middleman again and just skip from this first look of A, B to A double prime, B double prime. And then you can also see if we're just making those direct reflections across those parallel lines, then the line that goes all the way through the same point across it is going to be perpendicular to our parallel lines. So either the one going from A through A prime and A double prime, or the one going through B, B prime, and B double prime. They are all going to make right angles. They're going to be perpendicular. And the last thing to note is that in our translation from our A to our A double prime, like it says in this number 2, it's going to be twice the distance as it is between those 2 parallel lines. So let's look at this first example. So in A, it says to name any segments congruent to each segment. So first, if we look at GH, segment GH, it's going to be congruent with all the line segments that are reflected. If I reflect it, it's still going to have that same length. It's still the same size. It's still the same shape. So it would be congruent with G prime, H prime. And it would be congruent even if I reflect it again, it's going to be congruent with G double prime, H double prime. And the second one of HB, If HB is then reflected right here, this section of HB, it actually tells us that it's 9. If H is directly reflected across that line of K, then it's going to be the same exact distance away from it on the other side. So this one would also be 9. So in this case, I can say that HB is going to be congruent to BH prime as well. It's directly reflected across it, so they would have the same length. Same thing goes for GA. GA, when it's reflected across that line K, G prime is going to be the same distance apart from that line. So I could also say that G prime A is congruent with GA. Then if we look at B, it asks us if AC is equal to BD. So AC is this length here between our two parallel lines. And then BD is this top portion here between our two parallel lines. Well, since we know that these lines are parallel lines are always equal distance apart. So yes, AC would be equal to BD because lines K and M are parallel. Parallel lines we know are going to be equal distance apart. And then we know that A and C, in comparison to B and D, they're in the same position because since these are reflections, it tells us that these make right angles. And so if they're right angles, now we can look at this as being like a rectangle. So for this last one, what is the length of G double prime? So I'm looking for my G double prime length. I would want to label what I know. So I know up here that HB is 9. I know that DH, or DH double prime, is 4. And I'm looking for G double prime, this total length here. So if we know that HB is 9, earlier we said that BH prime would be the same length, so this side would be 9. Same thing can be said on the right, that if DH double prime is 4, then H prime D would also be 4. So that would mean the distance between our parallel lines is going to be a length of 13. And then remember in our last slide, if we go back for a second, the distance between our first letter, our original, our pre-image, and then our double prime image, it's going to be a distance of 2 times the distance between our parallel lines. So in this case, if our distance between our parallel lines is this 13, G double prime is going to be 2 times that distance. So in this case, we're going to have 2 times 13, which equals 26. So then we also have reflections when we go across intersecting lines, so not parallel ones, but ones that are actually going to intersect. When we look at intersecting lines, when we reflect it across each one, it's going to just keep adding to that angle that's going to be between those reflected images. So in this diagram, we have that the angle of that point there in the middle, so our measure of that angle of KPM, or so if I had actual points on here, I'm going to put points on it so we know what we're talking about, the same thing. I'm just going to put points C and D. So I have points, measure of angle CPD. It would equal this X that's there in the middle. That's what they've termed it as there. So then if I'm talking about reflecting my AB twice, I'm going to reflect it across line K to this shape here, and then I reflect it again across line M. My angle of rotation between the original, my pre-image of AB, to my final one of A double prime, B double prime, is going to be 2 times the original. So in this final example that we have, example 4, we want to describe the single transformation from this F, this blue fish down here, to our F double prime. So we're going all the way around. All we're going to do is describe its transformation. Okay, well, we know that it's reflected. not only is it reflected once to this F prime, but then it's reflected again to our F double prime. And so when it happens to do that reflection twice, notice that our fish now is kind of angled in the same direction. And so this actually looks like a rotation. So our rotation in this case is going to be just like the slide we just looked at. When I go from this F to our F double prime, this angle between the two, if I were to pick a point on my fish, like say his mouth there, the angle between both of them would be 2 times the angle of my intersecting lines. So now I'm going to have 2 times my 70. And so that gives us an angle of 140 degrees. So all that is happening in this picture is it is rotated 140 degrees. So here, like I said, we're combining things. Technically, we reflected it twice, but that double reflection actually ends up in being one single rotation of making that congruent shape rotate 140 degrees. And so in this case, that would be our answer. From F to F double prime, it's simply rotated 140 degrees.